In this video, we're going to be talking about antiderivatives. So as it says here, finding an antiderivative reverses the process of finding a derivative. It essentially undoes the derivative by taking you back to the original function. The best way to explain that is through an example. So we have a function f of x equals 2x, and we want to find the antiderivative of that. Now, we use a capital F to represent the antiderivative. So capital F of x. The antiderivative is going to be x squared. And the reason for that is because if we take the derivative of x squared, we get 2x. So what we're doing, as it says here, is we are undoing the derivative. You start with a function, x squared, you take the derivative, you get 2x. You have 2x. If you want to get back to x squared, you have to take the antiderivative. So they're inverse processes, the derivative and the antiderivative. Here's another example. F of x equals 3x squared. So using that same intuitive process, the antiderivative should be x cubed, because when we take the derivative of x cubed, we get 3x squared. And so we're doing these from an intuitive point of view. Let's just try to make sense of basically what we're doing. One more example, which will demonstrate this idea of a collection of functions. F of x equals 4x cubed. Well, it would make sense that the antiderivative is going to be x to the fourth. Because if we take the derivative of x to the fourth, we get 4x cubed. However, what is the derivative of x to the fourth plus 1? Well, the derivative of x to the fourth plus 1 is 4x cubed plus 0, or 4x cubed. It also has a derivative of 4x cubed. Well, what if we had x to the fourth plus 2? Well, the derivative of that is 4x cubed. In fact, x to the fourth plus any constant c, the derivative is going to be 4x cubed. So if we want to find the antiderivative of 4x cubed, how do we know which one of these is correct? Well, we don't. There could be a constant, or there may not be a constant. The constant might be 0. So to compensate for the fact that we don't know if there is a constant or what the constant is, we just write c. And so we would say that the antiderivative of 4x cubed is x to the fourth plus some constant c. So hopefully that makes sense. Now, the notation. The indefinite integral is the process that we use to find an antiderivative. And so we have some notation. We have these, that little squiggly sign, which is basically a summation sign, which we'll talk more about when we get into another topic. And then we have the dx. They kind of go together, and then in between we have the function. So to write it properly, you have to include the squiggly line, and you have to include the dx. So all this is telling us, when you see this, is, hey, find the antiderivative. So here's some problems we've actually already done, but now we're using the proper notation. This is saying find the antiderivative, or the indefinite integral, of 3x squared dx. And so we already know what we're looking for is the function whose derivative would be 3x squared, which is going to be x cubed, and don't forget to add the plus c. Same thing, the indefinite integral, or the antiderivative, of 2x would be x squared plus the c. Now here's one we haven't done, 8 dx. So what function, if we took its derivative, would we end up with just 8? And I'm thinking 8x. If I take the derivative of 8x, I end up with 8. And so if we have the indefinite integral of 8 dx, the antiderivative is going to be 8x plus c. So again, we're working backwards. But we can only work backwards from an intuitive point of view so long. Eventually, we're going to get to some more difficult problems where we have to have a rule. And so that rule that we're going to start with is called the power rule. And so we had a power rule for finding derivatives, and now we have a power rule for finding antiderivatives. And so this is the basic power rule whenever n is not equal to -1. So when we're taking the antiderivative of some x raised to the n power dx, what we do is we take the x, we add 1 to the exponent, and then we divide by that. That's the basic rule. So you can see that here, the antiderivative, or the indefinite integral of x to the fourth, would be x to the fifth divided by 5 plus c. The indefinite integral of x to the -5, we add 1 to the exponent, divide by that, plus c. And of course, these are not simplified, but the objective here is to just use the power rule. Okay, here's one where we have to use the special rule, which I kind of skipped over here, is when n is equal to -1. And I'll show you why that is in this problem. So it says here in the solution that the indefinite integral of 3x to the -1 dx is 3 log of x. Well, let's see why that is. If we have a function, f of x is equal to the 3 times the log of x, and I ask you to find the derivative of that, well, you could find the derivative pretty easily. It's going to be 3 over x. And so we're working backwards. So whenever you have a 3 divided by x to the first power, the antiderivative going backwards is going to be 3 times the log of x. So remember that 3 over x can also be written as 3x to the -1. So this would be the antiderivative version of the log rule for finding derivatives. A few more rules. These are kind of the inverse of some of the rules you already know. We're not going to worry about this one. We know that the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. We know that the derivative of b to the x is b to the x times the natural log of b. So now it's similar, but the antiderivative of b to the x is b to the x divided by the log of b plus c. So let's use those in a few problems here. So first one is pretty straightforward. The antiderivative of 2e to the x would be 2 times the antiderivative of e to the x, which would be 2e to the x. The antiderivative of 5 to the x is 5 to the x divided by the log of 5 plus the c. Now in more, the plus c is added for you, so you don't really need to worry about adding the plus c. It should be outside the little box that you have to write the answer in. There might be a couple where it's not, but for most of them, I believe it is. All right, even more antiderivative rules. These are what I refer to as the intuitive rules. I'm not going to really go over these rules. They have similar rules for finding derivatives. We just kind of use these without actually thinking too much about it. That's why I call them intuitive rules. Going to switch to red. All right, so the antiderivative of 4x squared plus 5x minus 1, we just do this term by term. The antiderivative of 4x squared using the power rule is 4x cubed divided by 3. 5x, using the power rule, the antiderivative is 5x to the second divided by 2. And now let's think about this minus 1. Why is the antiderivative a negative x? Well, if I have a function, negative x, what is the derivative of that? Well, the derivative of that is -1. So we're working backwards. And this one, again, we can go term by term, applying the power rule. Once we get down here, we have to start doing what we did when we were finding derivatives, which is to rewrite the problem so that it's in a form where you can actually apply the power rules. So with this one, we would write the antiderivative of x to the 1/2 power plus 3 times x to the 1/3 power. And then from here, you would apply the power rule. Be careful when you have fractional exponents. You're adding 1. So you're going to have x to the 1/2 plus 2/2 is 3/2 divided by 3/2 or times 2/3 plus 3 times x to 1/3 plus 1 or 3/3 would be 4/3 divided by 4/3 or times 3/4. And that would give you the 9/4. And so this was the answer that you will end up with once you simplify it and put it back in the proper form. With this last problem, again, you need to rewrite it. You need to get all the variables out of the denominator and into the numerator. So you're going to need to write this as the antiderivative of x to the negative 1 plus 3x to the negative 2 minus 2x to the negative 3. Once you have it in this form, you apply the power rule, except for the first term, that's going to be the log rule. And then you put it back in the same form as the original problem. Okay, that's going to be it for this video. The rest of this set of notes are application problems, and I will do another video on application problems of finding antiderivatives. I'd also like to know if anybody finds this type of a video useful. If you do find it useful, I will do more of these. If nobody finds it useful, I'm probably not going to do any more. So what I need you to do, since this is going to be posted in YouTube, is write something in the comments below and do that thing where you hit the like button, I guess. So hit the like button to tell me that you like this video. Write some comments, and if I get some positive input on this, I will do more of these. If not, this is probably the only one I'll do. Maybe I'll do the one on the applications. So it's up to you guys. Let me know how you feel about this. All right, bye-bye.